We need to talk some about this concept of capillarity, which is the phenomenon that enables the capillary fringe to exist. It's part of the reason why water is able to be sucked up above the water table and occupy the pores within the unsaturated zone. And to explore this, we're going to appeal to a diagram or a picture that's going to depict an experiment that you could do on your lab bench. So imagine that you had a tray, a big tray of water, and in this tray of water, you put in a narrow tube that's open on the bottom and is also open on the top. Then you fill your tray with water, and the water here, this tube is much smaller than, it's much narrower than is depicted here, and it's small enough that the water is actually pulled up into it due to this process known as capillarity. And the water will have some curved meniscus here where it contacts the walls of the tube and where it's exposed to the atmospheric air pressure. So there's water everywhere in here. This is all water in here, right? And then there's water in this tube and there's air on the outside. If we were to define some heights here, let's call this level 1 and call this level 2. And then define some particular terms here. So this is going to be air on the outside, and we've got water here. We know, for example, that here the pressure is going to be air pressure, and therefore the pressure of the water here where it's horizontal, PW2, is basically going to be equal to air pressure because this is a long horizontal surface here. We also know that up here, inside the tube, we're at air pressure, right? And the question that I want to know is, what is the pressure of water right here under this curved surface? And I'll call this PW2. Sorry, PW1. Okay, so we know here, because this is a long horizontal surface, we know that the air pressure is basically equal to PW2. We also know that the pressure up here, PW1, that because this is at the same level here, this pressure PW2, it applies to this surface, but it's also applying to this point right here at the bottom of the tube inside of the water. So PW2 is going to be equal to whatever the pressure is up here plus the weight, the pressure caused by the weight of this water column. So PW1 plus this distance here, which we'll call H sub W. H sub W times the density of water. This is not pressure, this is a rho, times Earth's gravity here. If we rearrange this to solve for PW1 and we substitute in P air for PW2, we get the following. PW1 is going to be equal to P air, which we've substituted in here, minus HW rho WG. If we're referring to pressure in gauge pressure, then P air by definition is 0. And so we know now that PW1 is equal to negative HW, the height times the density of water times gravity. if we look at each of these terms, individually, these are all positive terms. And so the fact that there's a negative sign here means that the pressure of the water just below this meniscus is actually less than atmospheric pressure. In a sense, this water is under tension, or it's a negative pressure relative to the atmospheric pressure. And so we can say here that the water in the capillary tube, especially towards the top, is under tension or relative to the atmosphere, it's at negative pressure, if we're using gauge pressure, or it's experiencing suction here. And so that's what this analysis of the capillary tube reveals, that water can exist under tension, and it can have a pressure lower than atmospheric.